Hi, I'm Abhilash. I'm from the compiler team of Intel, and today we are going to discuss about parallel algorithms, ranges, and oneDPL, which is also known as Intel ParallelSTL. The agenda of today's talk is going to revolve around three proposals. One of the proposals, which got recently, already got a vote of confidence, C++ parallel algorithms, that is P2300, and its follow-up on P2500. We will talk a little bit about the senders and the receivers concept, which is very important for parallelization, asynchronous programming. We'll be talking about P3179, which is about parallel range algorithms, which tries to infuse different kind of concepts related to schedulers on STD execution. And we are going to talk about industrial use cases, which involves oneDPL as well as NVIDIA's Thrust, which performs data parallelization and different kinds of modifications of the data algorithms, parallel algorithms. And at the end, we are going to look at some of the challenges which lay before us, as well as some question answers from the community in general. So at the end, the agenda of this talk focuses on understanding the core concepts of sender receivers, parallel algorithms, and how can we best consume what the standard library has in terms of accelerator codes as well as our CPU runtimes. So moving to the first topic, which is the C++ parallel algorithms, P2300. Before we go into that, so a brief history of where parallelization and the concurrency in case of C++ standards came into the picture. So from the C++ 17 standards, we have proposals on concurrency. We have the memory model, and which provides the initial concept of parallelization. Then we move on to the C++ 20 standards, where we had the advantageous uprise of concepts. We had the rise of ranges as well as modules, and which gave so much to the industry in general in terms of asynchronous task scheduling, linking different kind of components together, and running all types of asynchronous data parallel algorithms, which are needed for different kind of compute intensive workloads across our accelerators. Moving to C++ 23, the idea is to have ranges plus, which includes many ranges, as well as multidimensional spans. And going forward to C++ 26, we hope to see more of senders, receivers, and executors, reflections, and of course, different kind of algorithms and concurrency, more to be added inside the standard library. We are going to talk a little bit about how linking happens inside different kind of senders and receivers, the glue which helps to maintain asynchronous tasks like scheduling as well as execution down the line. And eventually, there are many proposals currently which are there, which focus on having device-specific senders, senders and receivers for accelerator runtimes. And we're going to focus a lot of that today in our talk. So what was the motivation behind P2300? The first motivation was the need to have a kind of like a flexible abstraction for where our code will be executed. That is the point where the concept of execution context came into our mind. So it can be on not only on the CPU, but it can be on the GPU. It can be on other hardware devices, let's say FPGA even. So assigning or binding a particular algorithm, data parallel algorithm, to a particular context where it should run was vital in the current needs of the industry. So the limitations of the current execution policies in specifying hardware execution contexts is quite prevalent, because the standard thread library, or even the future or the promise instructions, or rather I would say the implementations, are very crude level implementations, in the sense they offer very high fine-grained control, but they do not cover all of the test cases that rises when we are scheduling parallel algorithms across different hardwares. C++17 parallel algorithms are definitely a good start, but there is no control whatsoever over the hardware that we are going to run on. That is what the talk focuses today. Then rose the concept of something called as senders, schedulers, receivers. The concept of schedulers was to have different kind of async tasks scheduled from a main or a centered, or I would say the main task, which can delegate different kind of resources and delegate those resources or tasks to separate asynchronous threads which are running in parallel. And the main need for this kind of integration rose from the fact that C++ parallel algorithms offer parallelization, but they lack a control over the executing hardware. So if we have the schedulers which can specify an execution context where it can run, then it would be very much easy to schedule any kind of asynchronous tasks on those hardware without having to rely on any kind of memory leaks or anything which is happening upon, let's say, on the if you're running anything on the device side, you do not have to worry anything which is happening on the CPU side as well. So P2300 introduces the scheduler concept, which represents execution contexts as well as the where. The integration of these two is very crucial for the industry to move forward and combine our hardware capabilities. So before we move into a little bit depth, so this is just a very simple hello world example which was taken from P2300. So we have a scheduler. Now this threadpool scheduler is just a sample scheduler. You can have schedulers based upon different device contexts, for example, CUDA context or SYCL context or any other accelerator context. So the sender is something which is, as the name suggests, is its task is to send a particular data packet or a piece of information to an asynchronous task. And it needs a scheduler to assign those data to perform or to delegate that data to that particular task, asynchronous task. So here we have a simple let's say a sender on that scheduler. And we are just passing a simple std print or an std cout where we are querying for an int and we are returning a value which is 13 as of now. And so the end product of this sender is then contemplated by this then operator, which returns the argument that you get as 13 plus 14. And this last argument is, since the entire sender and receiver's architecture is asynchronous, so we have to provide something which waits or provides a synchronization on these asynchronous threads. So this thread sync wait is something which was introduced in P2300, which submits the async pipeline and waits for it to complete. Now, the sender algorithms can vary a lot. Here we have a simple example of just adding to asynchronously to 42 another integer, but it can take different kind of complex examples like standard reduction, standard transformations on different kinds of vector containers, as well as other data structures. So before we move forward, we have three different kind of sender APIs. So one kind of API is known as sender factory APIs. The other kind of APIs are known as sender adapter APIs, and the third one is known as sender consumer APIs. So these are all user-facing APIs. So factory APIs, the idea was that these are simplifically the factory design patterns of certain APIs. So you have the schedule and the just API, which are responsible for delegating the schedule as well as allocating that particular task or synchronous task to the receiver in a decade format. So by decade format means these happen lazily. So as soon as you start your execution context, you create a threadpool scheduler or any kind of scheduler. When you assign a schedule, this asynchronous assigning happens in a very lazy manner. So it can include various kind of optimizations in this lazy manner. So you can combine 2-3 different sub functions into one function while delegating this asynchronous sender function. So the API usage is like so. So you have the execution sender auto schedule, which inherently implements the scheduler, the auto scheduler, and to use it, you call execution scheduler. You create an instance of auto variable of that. You get the system thread pool, or it can be any kind of thread pool, and you instantiate that scheduler. So the schedule is the starting point of all of your sender asynchronous tasks. And the next is the just. The just is known to just send or delegate a part of a data which should be inside that particular scheduler. So what the sender needs to send to that asynchronous program that is executing. Then there are a couple of other APIs which are known as transfer just, just error, and just stop. Transfer just is almost a similar variation of just, where you just put in or delegate a data to your asynchronous sender in a lazy manner. But the caveat here is that you can pass in composite data as well. So depending upon your system threadpool, you can pass in here. The example we have seen, we can pass in 1, 2, and 3, but you can pass in any complex containers as well, which is denoted by this auto amp, the L value of these values. Then we have something called as just error, which just sends you like it is telling us to whether have this kind of executed or stop that particular lazy scheduling of that particular sender. So that means that, let's say if I want to send any kind of value or any kind of container to that particular sender, I have the capability to provide a error clause that it will fail in case if there is a type mismatch or if there is any kind of runtime errors. So just error and just stop, which provides the cancellation APIs, are just the nomenclatures of those. Then we come into the sender adapter APIs. So these are like building blocks which are put on top of your factory APIs, and they serve as intermediary layers before we pass them to the consumers, that is the user side. So for example, we have a lot of APIs inside the adapter list by P2300. You have the then operator or the then function, where you can return a sender by describing the task graph described by the input sender with added invocable. So that means that you can return a particular sender. So when a task is getting scheduled by an asynchronous sender or a scheduler, right, you can have the task graph described by the input sender, and you can add any invocable object on it. So this invocable object can be in any kind of container that you want. So this helps you to abstract runtime control over your scheduler. Then you have the upon star. Upon star has two caveats. So upon stopped or upon error. Both of them are similar to the then kind of pattern that we saw just now, but work with errors and stop signals. That means you have the capability to either stop it or stop that execution based upon any runtime errors, or you can throw some errors. Similar to that case is let. So let has three variations. So you have let value, let error, and let stop. They're also similar to them, but return the sender and performs callbacks. So that is where it gets different. So in the standard then case, you can send the sender with the invocable, but there is no callback added to it. So if you want to perform any kind of callbacks, then that the case that we have in the case of future unwrapping, which basically means that for a particular module inside the task graph, you can call back different other submodules inside that task graph. So this sender let value is used for that particular purpose. If you want to have persistent callbacks, which can do some subtasks together. Error and stopped versions are just the same nomenclature as we have with upon as well. So if you want to throw an error at runtime, or if you want to stop execution, then those are called. The next set of sender adapter APIs are probably the last ones. We have the on, we have the into variant, and we have the bulk and the split APIs. So the auto on will start, the provided sender on any execution agent belonging to a particular context by the scheduler. So and the into variant is sending a variant of the tuples of all possible sets of types sent by the input particular sender. So the difference between these two attributes is that on will schedule or provide the sender to a particular, let's say one thread is performing an asynchronous task. So that agent, bounded by a particular context, will be will start as soon as you call on the on function. So as soon as on is called, the initiation of that particular agent for that particular context will get created. But in the case of into variant is something which is very different. Into variant sends a variant of the tuples to all the possible sets, which is sent by the input sender. So that includes all the invocables that you have sent to a particular asynchronous task, and this helps to. And the use case of this is that you can manipulate or modify each and every entity within that particular tuple. Bulk is a very strong API, which is a sender, as the name suggests, is a sender describing a task of providing the function with every index in the provided shape along with the values sent by the input sender. So it is almost similar to the into variant, but here in the case of bulk, you have the capability to send multiple kind of invocables. That means you can specify the size, you can specify any other complex structures, you can specify any other data types to be sent in a bulk format. Split is another kind of the reverse of actually of bulk API, which returns a sender if the provided sender is a multi-shot sender. Now, before I get into this multi-shot sender thing, senders can be broadly divided into two aspects. One are single shot and one is the multi-shot. So single shot tensors, they basically include a single data structure or an invocable that you want to pass in. For multi-shot kind of sender patterns, you can pass in different kind of invocables or even a collection of different kind of invocables. So that is where the split comes into the picture. Only in the case of multi-shot senders, you can have a sender, you can split a sender into several other subsenders to perform any kind of fine-grained optimization or programming on them. Then you have the transfer when and the when all variants, ensure started and the stop task variants. So these are the other variants where transfer is very much similar to the transfer API. So when all of the, for example, when all returns a sender whose completed value is a provided scheduler on which will the provided sender on an execution context belonging to a particular context by the scheduler. So that means that when all is called, when a particular execution context has completed executing on all the invocables or all the tuples which is there. And this has certain variations. So for example, when all and the transfer when all is a submodule of when all. Actually, when you have completed all of the details of a particular when all operation, and if you want to transfer those invocables to another sender API on the same scheduler, then you want to perform a transfer when all. That means it will transfer the entire tuple collections or the invocables to that particular secondary sender. Then you have something called as ensure started. Ensure started, as the name implies, is just a check to provide whether the sender has connected through the execution context and is in an operational state. So these are some of the sender adapter APIs. Now, what is important to us are the consumer APIs. According to P2300, so we have the start detached and this thread sync wait. So start detached is almost similar to ensure started in the sense that they do not return a value, right? They do not return a value. In the case of ensure started, you will get a value whether the sender has actually started or it has got on execution connect or not, or whether it has connected to an execution context or not. But in this case, you do not have a return value. So if the provided sender returns an error instead of a value, then std terminate is called. Auto sync wait is, as we saw in the example earlier, is a sender consumer that submits the work, and it is basically a kind of like a synchronization module, which performs a check. First check happens that whether ensure start has worked. That means the sender is in operational condition on that execution context, and the current std thread or the std main thread is completed or is work in progress. So if it is completed, it will return that optional tuple value to the output, right, of that particular sender or the scheduler, and it will wait for that, or else it will wait for all the asynchronous tasks, subtasks to complete. So this can include any tasks which are submodules. So if we recollect, so in the adapter APIs, we saw certain callbacks being called. We saw certain values called as transfer. So if a module or a submodule of a sender is transferring some delegations to another sender, which is within that same execution context, so it will wait. So this particular function will wait until that entire thing is completed and the synchronization is there. So for us, these two, from the consumer side of the APIs, this is where it gets interesting. Now that we know about the sender's pipeline, that means the three individual components from the factory model to the adapter model to the consumer model, we can say some of the important features of senders and receivers. So senders represent work which is composable through sender algorithms. They can be forked or they can be joined. Senders can be multi-shot or single-shot, as we talked about. Sender factory and adapter models are lazy, and they support optimizations, and they support cancellations of the scheduled tasks. Many senders can be trivially made awaitable, and all awaitables are senders. This is a very important statement in the sense that so the last consumer API is where it gets interesting, because all awaitables are essentially senders which are waiting on a synchronization block. Receivers are like glue to the entire sender structure, and we are needing an execution context, which is a kind of like a customization point, which serves as a connection between your senders and the receivers. Like I mentioned before, lazy senders, they provide a certain kind of optimizations for us by fusing multiple functions or callbacks, which can be submitted by a single execution context. Then there are two capabilities which are very important: customization transfer with schedulers. So the transfer function in C++ does not allow direct customization by the target scheduler, because specialized schedulers, I would not say specialized schedulers, but let's say schedulers which are device specific or accelerator runtime specific may require specific calls for transitioning between CPU or device contexts. So to address these, specialized schedulers can inject a sender handle to transition from the device context to the CPU context. And this is where it gets very interesting, is that we will see some examples down the line where we are having device policies for execution context as well as host policies for certain accelerators. And introducing scheduler from adapters. So to enable full customization of transitions by both the source and the target schedulers, the proposal also introduces a schedule from adapter, which takes a scheduler as a sender as arguments. Now, this only helps for the accelerator runtimes in the sense that during transitioning, the schedule from, so the parent of that particular scheduler or the parent of that particular sender adapter is also sent as details to your GPUs when sending from your host to the device or any accelerator. So the default implementation of transfer, that is SND, the send and the scheduler, is equivalent to schedule from scheduler to send. So that means that it is just like a kind of like a parent-child relationship where you are sending your execution context from your host to your device. So this is an example of the sender's consumers part. So here we have a very beautiful example from P2300, which shows us the piping principle in CUDA execution context. And now this piping and this sender consumers example holds true for exceptions are when all kind of adapters are used. So except when all variants or on adapters are used. So in this example, what you're trying to do is you are trying to pipe different kind of submodules, different kind of simple mathematical computations one after the other. For example, in the first scheduler, you are calling the threadpool of your CUDA. Here the threadpool is invoked from CUDA. Sorry. To return 132. So in the next case, you are passing a new CUDA stream with an execution context, which returns a multiplication of 123, which with respect to 5. Now, this is a piping operation on a submodule of a particular sender, which is in on state, which has already been started. The same can be delegated to another, another submodule or another sender, which is connected through execution then using an input delegate I to return I minus 5, right? So the output of these three piping operations is going to return, essentially 123 into 5. and then it is going to return I minus 5. So you can definitely guess what the result is going to be. So piping helps us to compose different centers with a linear syntax. Without it, we would have to resort to nested kind of structures. And this example is very much interesting because here you are actually switching between your CPU thread pool, that is your host thread pool, to your CUDA streams, which is a device thread pool, and you are actually sending it back to your CPU thread pool. So this thread pool actually performs this scheduler from adapter kind of a representation. So from then scheduler, schedule from, schedule then, these kind of things then come into the picture, where you're delegating a particular input from your parent to your child. That means from this host to the device or vice versa. Now let us move into P2500, which is a variation of the and an improvement on the P2300. So the evolution of so the overview is that it tries to continue on the same principles of P2300 and advocates why it is important for to be present for C++26. And also discusses the integration of different C++ algorithms with the facilities in P2300. So before I move into this, let us see the design proposal. So the proposed solution in P2500 is extending the context, so the execution context, extending the concept of the scheduler to have a policy-aware scheduler. So, like I said, which was the core of this today's topic, is to have where and how this particular policy or this execution context is going to run. So the execute on function facilitates the creation of such policy-aware schedulers. So the design goal of this is to have extending the C++ parallel algorithms library with policy-aware schedulers, allowing customizations of different kind of execution contexts, and preserve the semantics of the classical C++ parallel algorithms, as well as the range-based algorithms. And minimal API changes. So it should be backward compatible, as well as it should be flexible enough to design or devise execution context when shared between host and devices. So the key features are combining scheduler and policy, and minimal and incremental API changes. So how the proposal is going to go about that is, let's say we are using a namespace std execution where we're initializing a vector. P3179, we are going to look at it a little bit depth. So for example, this uses ranges generate, which is the ranges API for this particular vector, and we do let's say a standard randomized distribution on it, and then we sort it, right? Now, in the case of P2500, we need to have certain kind of policy aware scheduler in this case. So we add for this execution context, we add on that execution we add some scheduler. So this scheduler is going to be either host scheduler or it can be a device scheduler. And we can perform the same kind of algorithms on ranges on the host as well as on their accelerator runtimes. So that is the design pattern of P2500. So why use schedulers? The reason is that schedulers represent execution context and they provide flexibility, and also they provide an API overview. So the key concepts are policy-aware schedulers, execute on, and of course the customizable functions. Actually, if we recollect, we said that the execution connect is a customization point, and we're going to use this feature for 3179 down the line. The execution policy concept defines the requirements of the execution policies. The policy-aware scheduler represents the entity combining the scheduler to an execution policy. The execute on, as we know, customization points binds the scheduler to an execution policy. So whatever we have heard till now about senders and receivers on standard execution policies can be applied over here as well. The additional point here is that along with this execute connect, like execution connect, you can also have execute on as a customization point, where in execute on, you can specify on which device or which policy, device-specific policy or host-specific policy, that particular sender or receiver is going to be worked upon. So this is an API example of that. So for example, we have the policy aware scheduler, which takes the, requires a scheduler of type name S. We have the base scheduler type. So this can be any kind of scheduler type. And we delegate a policy of type s.get policy for that particular execution policy. And how we are going to use that? Using the policy, policy type.get policy return. So here we can provide some, customizable execution policy types. So down in the examples, we'll be seeing we have something called as host device policy, or a oneDPL device policy. This will be seeing some of these examples down the line. And here, this is where you can actually add those device policies to perform the same kind of parallelization algorithms in the case of devices. So for example, this execute on functional API usage and example. So here you see we are having this namespace that we created, and we have this inline const expression where we have execute on function where we're going to execute. And this is where it gets incorporated into the usage. You have this auto policy aware scheduler where you are sending in the execute on my scheduler. My scheduler is a custom scheduler that you're going to put in for that particular device, and you're going to send in STD execution parallel. So you can pass in any kind of execution methods on it. So the standard library has a lot of execution methods: parallel, unsequential, and so on and so forth. So we have the capability to delegate all of those senders and receivers in the STD execution pipeline in that manner on that particular policy scheduler. So this is the existing API for up till 2300, where we have the for each API, which is collected on the execution policy and the corresponding iterator limits, first and the end, for a particular function f. The new policy will have this template kind pattern where you have this execution policy, iterator, and the sentinel for I. For any kind of operations. So sentinel for I can be, it can be for any kind of operations, let's say binary or unary operations. It can be for identity operations and so on. So for example, the const expression ranges for each result will have, like this kind of syntax. So ranges for each, you pass in the policy, you pass in the iterators, where the first and the last sentinels are the iterators, and you pass in the function as well as the projections. The new scheduler-based API is going to be, I'm not sure if it is visible down here. So you're going to have the scheduler, which imbibes that particular policy, and the rest of the arguments remain the same. So we have a couple of customization points. So the customization points is over here. So the policy execute on, where it can be a customization point, as well as you have the inside that execute on, you have execute connect, where there is another customization point. So due to this, you can have for each assigned to a particular scheduler with a policy aware binding, a binded policy for a CPU or the host or device, and you can, the rest of the arguments will follow as it is. And now this is another example of blocking similar to C++17 algorithms. So here we have the policy aware scheduler, we have the forward iterator and the function. We check, we use the for each function for each scheduler. We have the forward iterators, and inside that we see this scheduler execute this. Now it is very interesting to note that this will be delegated as an asynchronous task by itself, right? And this allows us, this scheduler, which is policy defined, allows us to dispatch it on a particular runtime, right? So you can we use execute on in this case as well? So you can also use different kind of sender adapters over here as well, like we mentioned before. So so we have two kinds of customization points in this case. One is over here, and the second one is over here. So this allows. So the question comes up is that if it is binded to a particular policy and this is executing asynchronously, who will perform the kind of sync wait kind of thing? So it is interesting to note that when the scheduler is executed, right, you are required to have a sync wait after that, and that is also present over here. That is also needed over here to synchronize the results of a particular output of a particular sender call for a particular policy-aware scheduler. So using the API is very much straightforward. So it is as it is. So you call a std for each, and you call the std execute on your GPU scheduler. Whatever std execution algorithms that you want to use, whether it is unsequential parallel or normal parallel, you pass in your iterators or your sentinels, and you pass in as a lambda to your item that you want to process further. So this is how the usage of the API is going to be. So like I said, parallel algorithms are customization functions through the policy-aware schedulers. You have the flexibility to form platform-specific optimizations. Now, this is another example where we can apply the same logic for a CUDA-specific scheduler. So here you see inside the namespace CUDA, we have a const expression tag invoke, where where we are checking for different tags. And inside that tag, we have the ranges for each implementation, followed by the corresponding CUDA scheduler where we have. So inside that scheduler, we are passing a particular CUDA kernel, and we perform different kind of operations on that particular kernel, and so on. The interesting idea is the same pattern can be used for any kind of non-CUDA accelerator as well. The idea is that here we are using tag invoke, which is essentially a kind of like forward declaration to whatever schedulers we want to use, or whatever execution context that we want to use. Now, the idea was that if we recollect, the idea was that it should be backward compatible. It should follow the classic algorithms as well as the range-based algorithms. So customizable algorithms are defined in std ranges. We saw a couple of examples on that. So parallel and range-based algorithms integration with schedulers. And the possible implementations includes, you can have the default and the customizable implementations using tag invoke by forwarding. You can extend the existing implementations with new kind of execution, like let's say algorithms, data parallel algorithms. And the examples that we saw is the std ranges for each. Is the same example that we can use over here as well, and over here as well. Now, to give you a brief understanding of how this is working, and to give a better understanding of how it is working with the customization points, this is how the design is going to be, or rather is. So you have the namespace ranges. You create a for each function struct, which is a templated, which calls a templated policy-aware scheduler, and the same kind of parameters which we talked about. We call a projection on that, and we use that particular for each result individually, right? So the same thing that we talked about in the previous two slides. So the benefits is that it provides a unified API for different kind of execution contexts. It provides optimized implementations per platform. It is extensible for future scheduling needs, and covers both the iterator and the range-based algorithms. There are certain open questions. I will come back to the open questions in the later sections. So the summary, as we know what it was. So next we move on to P3179, which is an addition or an improvement over P2500. So what are the key modifications here? So the parallel range algorithms should be close to the C++ classic 17 classic ones with minimal changes. The range algorithm should return the same type. That means it should preserve the semantics of the return type as the corresponding serial range algorithms. The proposed algorithm should be non-ADL discoverable, which is very important, and same as serial range algorithms. The required range and the iterator categories should be random access, but for all, but std execution sequential execution policy. So apart from execution sequential, you can have random access, and it should be possible to have the sentinel or the iterator, range iterator cater to that. The proposed API should require any callable object to be passed as an algorithm to have const qualified operator. This particular 3179 does not have the parallel range algorithms to be a customizable point, and this is not a const expression. So how do we switch from the parallel range algorithms to using P3179 kind of execution context and so on? So we have the for each implementation where we pass in the execution parallel and for an iterator over a container, and we do certain operations on this individual values of that particular iterator, let's say x. So here we are using an iterator and the sentinel. So we see that STD ranges for each, and inside that we provide an STD execution parallel. We provide the v begin, v end, and we do as it is. So there are minimal changes to this P3179. And we can use a range directly for this. So STD ranges for each, the examples that we showed just before as well, 2 slides before. So the same thing. What it results in is more expressive and unified calls, one of the most important advantages of having this. So let's say we are having a composite kind of pattern where we want to reverse based upon a particular device policy, execution policy. We are trying to reverse a particular vector or a kind of container. We are trying to transform it, and then we are trying to perform certain kind of multiplication operations with it. And here we can combine all of them through the piping instruction. We have seen a piping example before in the CUDA context for P2300. This is almost a kind of like an advanced version of that in P3179, where for any of the data which is present inside for the particular container binded to a particular execution context on a policy, you can perform all the operations one by one, piped together. So it provides a better expressive and unified calls together. So like I said, so how we are going to flow, how the progress is going through this in this case. So we already know C++17, we have the execution policy, you have the random iterators and all. So for C++20, you have the random access ranges and the projections, as well as the ranges APIs, and you can perform any kind of ranges operations, like just sort, reduce, transform, whatever. In this case, for 3179, we add an execution policy to the existing C++20 template of keeping everything else the same. So you have this random access range R along with the projections and the STD ranges APIs, and we use that execution policy context for those particular ranges API. So why it is needed? So why combine parallelism with ranges? So ranges offer a productive API with opportunities for optimization. Users are already aware of using C++20 ranges with non-parallel range algorithms, integrating execution contexts with different kind of execution policies. And this can the effects of this is twofold. So you can have the parallelism of a standard library, and of course lazy computations that we saw in the sender adapter methods, as well as the sender factory methods. Or you can have the C++17 ranges algorithms, which does not directly integrate with the parallel algorithms, which just does not directly integrate with the ranges. So the paper proposes 3179 of adding these parallel algorithms that combines all of those features together and work directly with the ranges. This is very much important when we go to accelerator runtimes, where this kind of algorithms needs to be offloaded to certain policies, and where we want to use this kind of range-based schedulers, the ranges API using the schedulers for certain device contexts. So we already talked about the design, just overview. So the execution policy parameter is added to the ranges algorithms. Introduction of bounded ranges for better parallel performance. So we have execution policies, random access ranges that we talked about. We have bounded ranges and algorithm return types. So these four features should be consistent with the standard ranges algorithm. So the enable single call fusion for multiple operations we saw in the piping example, and preserve the expressiveness of ranges. So these are another set of examples where you can use the STD ranges execution policy on certain operations. So here it is a indirectly unary invocable operation, of function on a projected function. So it requires the sentinel iterators, and you can use that ranges for each on this execution policy. You can perform this function f, which is a unary invocable function, as an argument, and you can pass in the runtime policy and the ranges or the sentinels iterators as well. So the differences lies in the fact that we do have a little bit of differences. So the parallel range algorithms require random access ranges. This is something which is a little bit different. The output can now be a range instead of just an iterator. So you have the flexibility of that as well. If you want to return a range instead of an iterator, you have the flexibility. So this is another example of fusion. So like we already saw the fusion example of piping a few moments before. This is another different kind of an example, almost the same. So you have multiple parallel algorithm calls. We also saw an example where we can change the policies, right, from the host to the device through execute on. But here we are only interested in the ranges fusion example. So here we have the reverse API, you have the transform API, and we are combining this together. So here you have the ranges API of any of designed on a particular policy. You are performing the views reverse piped with views transform, and it will give you the same result, which returns as the you have the capability to return an STD ranges or an STD standard output, like an auto output here as well. So this is just a fusion example that we are taking a look at, and the examples and the benefits we already talked about. It will help more expressiveness, unified code format. We can leverage all the C++20 features, bounded ranges. We can also return different kind of ranges, which is not a possibility currently, and more expressive code and potential for better performance. Now let's move into the device-specific use cases. So first is Thrust. So Thrust is an NVIDIA library which performs data parallel algorithms and different kind of optimizations. So the Thrust library is built on top of the CUDA library as well as the OpenMP and TBB, and provides many general purpose parallel algorithms in the C++ library. So it is one of the inspiration points which led eventually to the C++ standardization of P2300. So Thrust can be used to perform different kind of parallel operations, such as reduce, exclusive scan, for each, gather, and different. So and has both host and device execution policies. Thrust can choose between different backends, CPUs and GPUs. So for the CPUs, it is through thread binding library from us, Intel, and to provide different kind of parallelization. Also, it has the OpenMP offloading as well, which is also used. So here we see a typical example from Thrust. What is the template of host and device specific execution policies, and how easy it is to create a structure, policy for your device specific execution policy and to call that particular policy. So this is the example of a host policy, and this is the example of a device policy. So you have a particular template of a derived policy where you are creating a structure host execution policy, which takes your runtime Thrust runtime device execution from your Thrust runtime device execution pool. So it can be a CPU as your host, and you have the execution policy, assigned to it. You return a structure for that particular policy, and you can bind that policy to run any kind of operations. So here you can perform reduce operations, you can perform transform, or you can perform gather, or any kind of collective operations you can perform on it. If you replace the host with the device execution policy, it will run on your CUDA GPU essentially, and will take from your Thrust host system namespace, which is going to be this will be Thrust device namespace, which will be your Thrust device, which is your CUDA GPU. Now we have the capability to bind this kind of policies with STD ranges as well through P3179. Same things happen in the case of oneDPL, which is Intel's ParallelSTL standard template library. So here you have the capability. So here it is a little bit different because unlike CUDA, we have something called as a SYCL accelerator runtime, which is almost similar to CUDA, has significant differences as well. And it is designed for not only the SYCL runtime, but also all devices assigned to it. So it provides parallel API mapping for SYCL kernels as well as certain macros, and provides different kind of vectorization algorithms as well as different kind of optimizations, similar optimizations that we see in Thrust. So oneDPL or the ParallelSTL is involved in different kind of device execution policies. We'll be seeing just now. In the case of CUDA, we had mainly host and the device execution policies. Here we have a couple because we support a little bit of a diverse range of the devices. So not only CPUs or our accelerators, but also FPGAs. So let's take an example look at it. So for example, this we can use the std C++ std execution policies as it is with oneDPL. So you can have std fill algorithm to work on the DPL execution. DPL execution is taken from the std C++ execution library. So you can use the standard C++ execution library for parallel sequential or parallel for your algorithms. And you can have the SYCL device specific properties, device SYCL device policies. So here you see a device policy which is on your GPU selector. So if you have a Intel GPU selector, Intel GPU in your ARC GPU or any kind of GPU, so you can use this policy, you can bind this particular policy to a particular Intel GPU device through this device policy. And you can perform any kind of ranges API or any kind of views as well. So here you have DPCPP default. DPCPP is like the data parallel C++ compiler for us. So we have, by default, it will take up whatever runtime DPCPP device that you have. It can be a GPU, it can be an accelerator, it can be an FPGA as well. So as we see in these examples that we saw is that there is a huge capability of all these proposals, starting from P2300 to P2500 as well as 3179, to be added to the custom device invocations as well. So that means in the device cases, we have the capability to add these features as well, right? So once we unify these ranges parallel algorithms for STD ranges, then we can leverage STD ranges through parallel execution policies. We can have customizable execution points like we saw in the custom senders, execute on, execute then. We can assign or delegate or send from the host to the device. We can allocate different kind of policies from the host or to the device and vice versa. So this opens up a lot of challenges as well as questions to the community as well. So first I will address the challenges. So the challenges are thread safety, the most vital challenge. Support for forward ranges, customization points. Is there a need to have any more customization points apart from what we already have? And interaction with schedulers. So P3179 has a very interesting take on the intersection or the interaction with schedulers. And the next steps probably include, for the committee as well as, from the design perspective, would be, as a suggestion, would be to finalize the API design. Thread safety is the major concern when it comes to asynchronous task scheduling, especially on instructions which are run both on the CPU as well as the host. So does the standard optimizations that let's say our compilers generally provide, will they allow us to perform thread safe instructions or not? Explore the integration with P2300 with respect to the schedulers and the execution context, and implement and of course benchmark. Is going to be always the method to go forward. So these are all that I wanted to cover inside my topic on the parallel algorithms, ranges, and some industrial use cases. I will be open for questions and for resources. There are only these three are the resources which are included in this particular for this particular context in this talk. So yes, that's all about me and my presentation, and especially thank you for attending.
Thank you for your talk, Abhilash.